So in this video then, I'm going to be running through some questions based on periodicity. So this is a rather broad topic in terms of first year A level, in that it just covers trends across periodic tables. So that includes things like ionization energies, as well as trends that go down the groups every so often as well. So it's all about describing how properties change based on the position on the periodic table. So we're just going to go through a few, I say, straightforward questions. A few questions that could cause difficulties and problems sometimes, and just focus in on how you're supposed to answer these and how you're supposed to answer these well. So we'll kick right off with this first one, which is quite a complicated one in the sense that it talks about ionization energies. However, it adds you to asks you to add the missing points for the elements across period 2. So it's given us lithium and beryllium as the first two, and it's expecting us to put in boron, carbon, nitrogen, and oxygen, which doesn't seem like a difficult task because hopefully from what you've done, what you may have learned, it's quite straightforward. The ionization energies of the elements increase across the period. So you may be forgiven for just looking at this and going, yeah, one nice, well, that is not a straight line in any sense of the word, but one nice straight line that connects them both. You might be forgiven for thinking that that is simply how it works. However, it's not how it works. It's never that simple because, as I've talked about in previous videos, we have electrons in these orbitals, and the ionization energy is essentially the energy required to remove them, and that energy will change, okay, based off of where you are. So for example, from lithium to beryllium, it's fairly straightforward. You're adding an electron into the s orbital. Okay, lithium has one electron in the s orbital, beryllium has an extra one. So if I put the orbital there, lithium is the first one, I'm adding the second one for beryllium, I'm adding to the same orbital, so it's the same distance from the nucleus, but the nuclear charge is increasing because beryllium has an extra proton, which means it holds it tighter, which means the ionization energy is higher. The problem is, as you go from 4 to 5, so from beryllium to boron, you're not adding an electron to the s orbital anymore, you're adding it to the p orbital. Now the p orbital is slightly further away, which means that actually when you do this line, beryllium to boron is actually a decrease. Only a slight decrease, and it's not sufficient to go below lithium, okay? So be very careful when you do this little decrease. It's a very small decrease, okay? And it's not below lithium, okay? So it's a very shallow decrease, and this is just because I'm now into, 5, 6, 7, all these extra electrons are going into the p orbital. So everything from 5, 6, 7, 8, 9, 10 is going into, I'll draw it underneath here, a p orbital. Okay, and that's further away. So my first electron goes in. Now, when my second electron goes in, that's fine. It's just being added to the same subshell, and you get a slight increase again. Just be careful with the slight increase. The slight increase needs to go now above beryllium. Okay, again, slightly above beryllium. Again, examiners will be a little bit picky on this. Okay, so when you add it for number 6, so carbon should be above beryllium. Then when you add the next one, it goes up again. Okay, because we're just adding another electron into the orbital. So we keep on rising, up to 7. And now we have a question to answer, because does it keep going up, or do we have something else going on? Well, the fact that I'm asking you probably should tell you what's about to happen. If you look at my little diagram at the bottom, the next electron I add is, yes, it's going to still be in the p orbital, that's absolutely fine, but you're going to be pairing up electrons. Okay, the electron is going into the same shell, well, the same subshell, sorry, the same orbital as another electron. So we're now filling up the orbital. Because we fill up the orbital, we get something called electron pair repulsion, and that isn't favorable. It's not a good thing. Electrons are both electrons are negatively charged. They want to repel each other, and so you end up with a slight difference in the ionization energy, because this time the electron doesn't really want to go into that orbital. So you get a slight decrease, again, a very slight one, And again, notice it's only a slight decrease, and it still has to be above what we had before. So it's below the 7th element, but above the 6th. And then when we add our next electron in, yes, we have some repulsion, but we already had some repulsion, so the effect is not as pronounced. So this time we get a straight line up, and it joins to fluorine and then to neon, as we've seen. So again, there's two key points on the ionization graph. We have a slight drop between 4 and 5, and a slight drop between 7 and 8. Now, luckily, in terms of exam technique, this is replicated if you go lower in the table. So if you drop down another row, down to sodium, magnesium, aluminium, silicon, etc., it will happen this way as well. You will have a slight drop between magnesium and aluminium, and a slight drop off between phosphorus and sulfur. Okay, in the same way as we have a drop off here. So this line looks identical the further down you go. It will just be at higher values, okay, or lower values, depending on where you are in the table. If you go up a row or down a row, will change where the values are, but the values themselves don't really matter. The shape of the line will always stay the same. So it then asks you 3 marks this. They give you a lot of lines to write on this, even though you don't need it. First, ionization energies decrease down groups in the table, so it's easier to remove successive electrons. All you have to do is explain why. So a bit of exam technique. Whenever you see this question, they're asking you about first ionization energy. So it's all to do with the size of the atom. So for the first mark, increase atomic radius is fine. Okay, you can, if you want, you can bullet point this, by the way. There's no reason to write prose in these exams. Absolutely not. This is not an English paper. This is chemistry. We don't care about English. Okay, I don't care about prose or fancy essays. Do it in as few words as possible. So increase atomic radius, or if you want, just write the words more shells. That is verbatim from the mark scheme. You will get a mark for saying that. That's the first mark on its own. The second mark is then talking about the extra, what else is going on here. So you've got large atomic radius. As you go down, you do have an increase in nuclear charge, which you would think would hold on the electrons more tightly. So increased nuclear charge. Okay, that's not a good thing for ionization, because that would hold it on. Higher nuclear charge, you'd think that holds the electrons more tightly. However, what you also have is more electron shells, as we said before. So specifically, keyword, more shielding. Okay, and you can write that the shielding is outweighing. Okay, so shielding, I'm just going to do a shorthand here. So the shielding, okay, is a greater effect than the nuclear attraction or the nuclear charge. Forgive my awful handwriting. So the increase in nuclear charge is outweighed by the increase in shielding. Okay, and therefore, overall, your final point, therefore, there is less nuclear attraction or less attraction. Let's put less attraction to electrons, and that's it. That's all you need to write. Okay, you might think that's a lot to write, but for 3 marks, it's a gimme, and you'll always get the same answer for this question. Okay, they're always the same marking points, and you don't need to go into much detail. Just hit the key points and move on. Notice you have, what's this, 1, 2, 3, 4, 5, 6, 7, 8, 9 lines to put this answer on. And all in all, I mean, I've done a pretty complete answer there. You could probably write a bit less than I wrote and still get all the marks. So just be aware of that. Okay, there's no need to go into essays. We're not in an English exam. We can write less and still score the same marks. The number of lines is not always indicative of how much you need to write. So going on then, there are properties now then. So bromine and mercury, okay, react to form mercury bromide. Here's some data in the table. Okay, the question then, this is the bit that actually matters. Describe and explain how electroconductivity occurs in mercury 2 bromide and mercury. This is a very easy thing to miss. You need to do mercury bromide and mercury in both solid and molten states. There's 5 marks available for this, and ironically very, very few lines. However, this should give you an indication really of how straightforward this is going to be. Okay, because ultimately, in terms of your electrical conductivity, it's fairly straightforward. Okay, it gives you everything in the table as well. So there's no real excuse for getting any of this wrong. So in terms of, mercury, hopefully, to get a couple of marks here is very, very, very straightforward. So mercury, so Hg, will conduct in both solid and molten. Okay, so mercury will conduct both solid and molten. I'm just abbreviating a bit here. Both solid and molten. And that is because, and you have to give a reason, so that's 1 mark by the way, both solid and molten states, because it has delocalized electrons. Okay, and the delocalized electrons can move. Okay, free to move. Delocalized electrons can move. I'll just put can there. Okay, delocalized, they can move, they can carry a charge. That gets you 2 marks immediately. Okay, this is very much a GCSE question if I'm being honest, but it's on an A-level paper. For mercury bromide, so for HeBr2, just be careful with the wording here. So mercury bromide, it will conduct when liquid or molten. So molten, liquid, dissolved, but it specifically says molten. So yes when molten. So molten, yes. Solid, no. And the reason is, okay, because when molten, when it is molten, ions move, or free to move, I should say. I put free to move. It's me trying to be lazy and write less. Ions free to move, and in a solid, ions fixed in place, i.e. cannot move. Notice the difference in the wording though, because in mercury, it's electrons that move, and in HeBr2, it's ions that move. This is a key part of your answer. You cannot afford to get these words confused. If you get these words confused, you're throwing marks away, because you cannot say delocalized ions for mercury, and you can also not say delocalized electrons for mercury bromide. Okay, be very, very specific. Okay, vague, or as I say, hedging your bets is never going to get you anywhere. If you write both down, it's got delocalized ions and electrons, the examiner's going to just simply mark you down. Okay, you can't hedge your bets at A level. They're not going to give you benefit of the doubt. They'll just put a big con on your answer and take the mark off you. Okay, if you contradict yourself, you get nothing. That's the problem. Okay, so don't hedge your bets. Learn what's going on. Okay, so in the ionic compound, the ions are moving. Okay, that is the straightforward bit. Okay, that's the straightforward bit to understand, but it's very easily forgotten in an exam. That will get you 5 marks. Simply describing it gets you 5 marks. Okay, the key part is obviously pointing out that mercury bromide conducts when molten but not solid. Molten, the ions can move. Solid, they're fixed in place. There's 3 marks for that section, and there's 2 marks for the mercury. Frankly, giving marks away, if I'm being honest. Right, last little one I will do then is a 4-mark question. Okay, are magnesium and silicon. They're very, very similar to the last question actually. Different types of giant structures, describe the bonding, include the names of the particles. This is very, very straightforward. So I'm not going to spend too long on this. But again, just to show you what you need to put down. Because it sounds silly, but there is a mark available just for saying that if you just write magnesium and then the word metallic bonds, or just metallic for example, metallic bonds, that's 1 mark. Okay, and then if you say what the bonding is between, because it says include the names of the particles and describe the forces. That's a really important bit. That's a really bad circle as well. But you've got to describe the forces. So what is a metallic bond? Okay, so attraction between, attraction between Mg2 plus or positive cations. I would be specific in this case because it tells you it's magnesium, and delocalized electrons. Delocalized D minus. That gets you the 2nd mark. It's easy, this, isn't it? And silicon is covalent. And they tell you in the question it's giant covalent, so you don't even need to write giant covalent. Just the word covalent gets you the mark. And The bonds are between the atoms, shared pairs of electrons, just literally bonds between atoms. 4 marks. All in all, I probably wrote about, I don't know, 10, 12 words there. They gave me, what, 2, 4, 6, 8, 9 lines, but you can answer it in literally a few words. So hopefully this has been a bit helpful in showing you exactly what needs to be put down in these sorts of exam questions, and hopefully the fact that specifically for these types of questions on periodicity and structure and bonding, into a sense, it's all about brevity. The shorter your answer, the better. Okay, just include the keywords, include your points, bullet point them if you need to, and that will get you all the marks. Okay, writing a ton of stuff down looks impressive, but I'm getting 4 marks for basically what I've wrote there gets you 4 marks. So why are you writing 9 lines? Not worth it. Okay, so hope that's been helpful. And like I say, that's essentially all you'll ever really get asked on this in terms of AS level.